So we're still on lesson 1-6, and today we're going to talk about two major topics. So what I want you to do is on, let's see, how do I want to do it? Let's do one side will be independent versus dependent variables, and that's the one we'll deal with first, and then we'll do the other side, still be lesson 1-6, but we'll talk about analyzing graphs. And then we'll do some follow-up with our papers to put in there. They're each their own set of notes, so you can put one on one side, one on the other. Okay. So let's start with independent versus dependent variables. And we're at 10:13 today. Okay, so first thing we need to do is, can you tell me what the word independent means? Michael.
By yourself.
Okay, so by yourself, you don't get any help from anybody, you're on your own. What does dependent mean? Okay, you have to rely on something. So we're going to use those ideas when we're talking about a situation that could be rewritten as a math equation, where we have independent variables, variables that are standalone, they do what they want, but based on them existing, it affects a different set of variables. And the second set is called the dependent. So let's do our definitions of an independent variable. Now I've got a half sheet. We'll have to see. It may take us more room. We'll just have to see how this works. So let's do an independent variable. And let's highlight that. Just like your book does. And an independent variable is, let's see. This is the variable that determines the output. So if he is the one that determines the output, what does that make the independent variable? He's the input, right? Okay. And if it's the input, what variable does that represent in equations generally if we have two variables? Jack? It represents the x. And if you think back to our terms yesterday, input and x relate to domain or range. Which one? Domain. So x exists, the input exists, the domain exists. And when we stick that domain, that input, that x, into our equation, we get out something. So that something we get is dependent upon what we put in. So that is our second definition, which is a dependent variable. Highlight him again. And so this is the variable whose, I know I always use wrong pronouns when it comes to, because whose means it's a human, and dependent variable is not a human, but I teach math. That's no excuse, I know. The variable whose answer depends on the value put into the equation. So what words are we talking about that would represent dependent? What other vocab words have we talked about that would represent dependent? Jack. Okay, Johnny Ray? Output. Number 1, output. And then what do we associate output with? Y. And what do we associate output and Y with? Range. Okay. So where this gets a little confusing is trying to read a scenario and figure out what's the core and what answer depends upon that core. So we're going to do a couple of examples, and then we'll probably leave this blank page. And then we'll come back and we'll add stuff to it. So let's see, do I have enough? Yeah, I'll just do it here. So our directions, we're going to keep it all on the same page, would be identify the independent and dependent variables. So first, the dance committee is selling tickets to the fall ball. The more tickets they sell, the greater the amount of money they can spend on decorations. Okay. So my job is to figure out which one is the independent and which one is the dependent. Sometimes I think it's easier to figure out the dependent. Which one of these scenarios depends upon something else happening? Okay. So again, the dance committee is selling tickets to the fall ball. The more tickets they sell, the greater the amount of money they can spend on decorations. So what are the two major variables in this problem? Just in general. Don't tell me which one's independent, which one's dependent. But what are the two unknowns going on in this problem? Patrick? Tickets. Number of tickets sold. And what's the other one? Money made, right? So number of tickets sold, money made. Everything else just was kind of telling you backstory. All right? So which one is the dependent? This one depends upon the other one. Okay? Joey. Okay, so the money, near you. This is going to be your dependent variable. Because how much money you make depends upon how many tickets you sold. So that tells us tickets that are sold, that's your independent variable. Does that make sense? Okay, I heard one yes. All right. All right, so let's go ahead and do one more. Oops. Maybe black would be good. Generally, the average price of going to the movies has steadily increased oops, I spelled that one wrong. Over time. Okay, so now I want to figure out what is independent, what is dependent. Okay, So what changed? What was the change? Which one is dependent upon the other? So first off, what are our two unknowns in this problem? What's one? Give me one. Throw one at me. Bianca.
Time.
Time is one. What's the other one? Yeah, the average price. So we've got time and we've got cost, basically. Okay? So which one would depend upon something else? Joy? Okay. What does the price depend upon? Yeah. Time is not affected by anybody, right? So the average price would be your dependent variable. And your time would be your independent variable, because time marches on and doesn't depend upon anybody to move, right? We can't stop time unless you're Doctor Who, right? And then you can, okay? All right, so for right now, let's halt on this one from here. And we're going to take the second set of notes. So we had 2 pages, looks like, for independent variables. One with the notes, one with the examples. And now we're going to a new clean page for notes. So we're like on our 3rd page now. Oh. We're going to be analyzing graphs.
We're still 1-6, right?
Yep. Same date. Okay. So analyzing a graph is to analyze a graph. Means to interpret a situation even if numbers don't exist on the graph. So you're used to seeing graphs that have scales on them, right? And sometimes you're going to get graphs that just have titles, but there's no numbers involved. So interpret a situation even if numbers don't exist on the axes. So I'm going to give you an example, and then you can work on it. And then I'm going to give you, for part of your homework tonight, you're going to have a worksheet, and your job is to take descriptions and pair them up with the graph. Okay? So this is got a title, bike ride. So somebody's on a bike ride. The only things we know is time is the horizontal axis, the vertical axis is distance. And normally we write titles that go the same direction as the axis. Okay, so that's distance. And the graph looks like this. Okay. So this particular graph represents a ride that a student did on her bike. And our job is to try to figure out what happened in the ride. So what we're going to do is look at it as pieces. So what happened in the red piece? What would you say was happening from the bike ride in the red zone? Okay. Michael, what do you think?
It went up.
Okay. So, but what went up?
Oh, the way went, how many miles?
Okay. What else, Jack?
Speed.
Okay. Speed could go up. What else?
Distance.
Okay. Distance go up. What else? Time had to go. Okay. So as time began, she had an increase in distance. Now we can't always talk about speed so much. We can look at slants can help us, but the key things we're going to focus in on are the two titles, time and distance. So in red, as time increased, her distance increased. Okay, let's talk about this part. Call him blue. So what do you think is happening at blue? What do you think was physically happening at blue? Is time going on? Or does time stand still? Johnny Ray? Time goes on, because time doesn't stop, right? Unless you're Doctor Who again, okay? Time goes on. But what did stop? Her distance stopped. So what do you think physically happened on this bike ride at this point? What do you think went on? Perry? She took a break. Maybe she rode her bike to a friend's house, and she's at the friend's house. So time's marching on, but she's not going anywhere. She's flat. So time increased, but distance was constant. So we could come up with a conjecture. She was off her bike. So during that blue time, she wasn't riding her bike. Time still goes on because time doesn't stop. Okay. What do you think happened during the green time? So what do you think happened during the green time? She got back on her bike and she kept going. So let's see. Let's say time increased. And distance increased. And so we could say, we could conjecture, she continued riding her bike. So that's what you guys are going to be working on tonight. Now here's what I'm going to say. This is kind of a challenging concept to gather. So go on your ebook tonight and go to the personal tutor that goes with this example so that you can get more examples, okay? This is going to be the best way to help you with this is practice. And then your homework tonight is going to have you practice as well. So